So the next speaker is Professor Will Polik from Hope College in Michigan, and he will be talking about WebMO.
Okay, moment. Let's see.
Kurt may have to stop sharing his screen so that you can share your screen possibly.
Right. See if we can make that happen.
Yeah, Professor Rocha, can you stop sharing your screen? Yeah, thank you.
I think I've done it.
Okay, all right, good, great.
All right, can you see my screen using OpenMOPAC?
Yes, yes, your screen is visible.
Great, good. Okay, then I think we're set. Give me one moment. And I'll start my timer. Okay. Well, hi, everyone. I'm Will Polik. I teach physical chemistry at Hope College in Michigan, and I'm a co-developer of WebMO software. I'll be speaking today on using OpenMOPAC and WebMO throughout the chemistry curriculum. I'm going to talk about three main things in my 15 minutes. First, why use MOPAC and WebMO together? Secondly, and the main portion will be to demonstrate a wide variety of examples of MOPAC and WebMO in various different courses at the undergraduate level. And then thirdly, describe a variety of methods for deploying MOPAC and WebMO together. So why MOPAC for undergraduate chemistry education? As has been mentioned, MOPAC stands for Molecular Orbital Package and has been under active development since 1981 by Jimmy Stewart with contributions from other coworkers. It's a semi-empirical quantum chemistry program and therefore very fast and capable of dealing with large systems. So it's quite versatile. MOPAC is known for its very direct and simple input file, and certainly compared to other programs, it's relatively readable output file. I've personally described MOPAC as the organic chemistry's friend when it comes to computational chemistry programs because of its energies are reported as heats of formation, with what we're familiar with, and the units are typically kcals per mole. MOPAC started supporting S&P orbitals from its outset, and then in the early 2000s, I believe, incorporated d orbitals, which now allow it to deal with hypervalent main group atoms and, of course, transition metals, making it extremely versatile. And as we now know, MOPAC has transformed into OpenMOPAC, which is being distributed on GitHub as open source. Another strength of MOPAC is its wide variety of calculation types, not only molecular orbitals, but also vibrational normal modes and infrared spectra, thermodynamic quantities, solvent effects, locating transition states, following reaction paths, and as we'll hear in our first talk after our break, MOPAC can now model excited states and UV vis spectra. Why use WebMO? Well, WebMO stands for Web Molecular Orbitals and has been in active development since 2000 by J.R. Schmidt, who is currently a professor at the University of Wisconsin at Madison, and myself. WebMO is a web-based interface to various computational chemistry programs. Its key feature is that users do not need to install any software on their computers. They just use their web browser and access the program through WebMO on a server. It's useful for novices because it's menu-driven and reasonable defaults are provided for most jobs, and also for experts, because one has full access to the input files and the output files. WebMO supports not only MOPAC, but a variety of other computational chemistry programs, and the basic version is free. Now, this is maybe a visual model of WebMO. On your server computer, you'll have your computational chemistry program, there's MOPAC, And then also WebMO, which is the interface between the computational chemistry programs and other users out on the web. So users communicate to WebMO via HTML, or HTTP, I should say, over the internet, and WebMO communicates with the underlying computational chemistry programs via CGI scripts. The point here is that we install it once on a server and then can run it from anywhere. Okay, why together? Well, as I mentioned, WebMO supports a wide variety of computational chemistry programs, or we call them engines. I will point out that only two here have the words molecular orbital in their titles, which is actually key to, I think, education and also an outgrowth of how MOPAC has been developed. On a perhaps more serious note, the end users need both an engine and an interface. So MOPAC is the engine, WebMO is the interface, and the combination is uniquely intuitive. Both are very user-friendly, versatile, can address a wide variety of programs, powerful, can look at very large systems in a reasonable amount of time, and low cost. Okay, I'm going to switch gears now and give you a few examples of using WebMO and MOPAC throughout the entire undergraduate chemistry curriculum. So let me switch what I'm going to be sharing now. Hopefully this will work. Maybe I can just go directly to here. Yes, you should be now seeing a WebMO login screen. Jonathan, can you see that?
Yes, yes.
Yeah, great. Just want to make sure that you can see what I can see. This is how one would log into WebMO. So I'm just going to log in as myself. We're actually logging into the demo that's hosted on the WebMO website. And the job manager is sort of the home page. And it's like your email inbox with your most recently run jobs near the top. We're going to run a new job and look into molecular shapes, specifically the shape of SF6. So let's draw a sulfur atom with 4 fluorine atoms attached to it. And WebMO knows how to use ideal bond lengths and bond angles, so it will do that for us to prepare our input structure. And you'll notice that the structure is actually, the axial fluorines are linear in the idealized sense, and this is a seesaw structure. But if we move on and use MOPAC as the computational engine, and there's some useful defaults, such as the job names, the chemical formula. We, though, want to do geometry optimization, and we'll use PM6, and we'll just simply submit that. It is now running. By now, it's actually done. So if we refresh, we can actually visualize the result. And at this level of theory, PM6, you can see that the axial fluorines are no longer exactly linear. They're slightly bent. PM6 captures the idea that the lone pair of electrons takes up more space than bonded pairs of electrons, consistent with VSEPR theory. In fact, WebMO parses out a lot of information from the MOPAC output file, including, for example, the PM6 heat of formation, also the dipole moment, which we can visualize. The dipole moment points towards the more electronegative fluorine atoms, and it's not along a bond, which is interesting for general chemistry students to understand. Okay, let's try another job, and that will be conformational energy scans. So we'll look at butane. We only need to draw the backbone because WebMO can add on the missing hydrogens and idealize the bond lengths and bond angles. We'll then define the coordinate to be scanned, which in this case is the dihedral angle, and define that to be scanned from -180 up to +180 in 36 steps. Each step will be optimized. So let's run that using MOPAC. It's a coordinate scan, and let's go. Once again, it's running. It's submitted to the internal queue of WebMO. It is done by now. and we'll take a look at it. A lot of things are parsed, not only, but here's the results of the coordinate scan, but we can look at it visually by making a plot. Now in WebMO, all the plots are interactive. So if you want to look at perhaps, what is, when the coordinate is 120 degrees, we can just click on this and we get a picture of it, and we see that that local maximum is in partially eclipsed geometry, where a methyl group is eclipsing the hydrogen. We'll do one more example, and that will be a spectroscopy example of acetaldehyde. So let's draw that. Again, we only need to draw the backbone. WebMO knows Lewis structures and things of that sort. And so here we have acetaldehyde. We'll go ahead and this time run a optimize and vibrational frequency job. I'll point out at this point that WebMO does give us access to the input files, so we could preview what actually is going to run. Here it is. So let's run that. We could have edited that if we wished. We'll run it. And again, MOPAC is so fast that we're done. And take a look at the output. I do want to point out that in addition to the parsed output, we have full access to the raw output from MOPAC if we wished. And so here, for example, are all of the normal modes and things of that sort. But what we're interested in is the infrared spectrum. Here it is as displayed by WebMO. And we can simply click on this very large peak around 1900 wave numbers and see that it corresponds, at least at the PM6 level of calculation, to the carbonyl stretch. So it's a great way in education to correlate spectral features with molecular features. In other programs, this also works for NMR spectra, things of that sort. Let me go back to the slideshow. So let's share that. Okay, I believe now you can sort of see the usage examples. We've already walked through the general chemistry examples of molecular shapes and dipole moments, and the organic chemistry examples of conformational energy scans and interactive spectra. In analytical chemistry, one can study different indicators. So this is an example of taking phenolphthalein in a acidic solution and in a basic solution and calculating the UV vis spectrum of it. And so here, where it's fully protonated in the acidic solution, it's transparent in the visible, whereas in the basic solution, where we've pulled off a proton, this results in two of the phenyl groups being conjugated. And so there are now absorbances in the visible that absorb the blue and the green area, resulting in a pink solution. In biochemistry, we can set up a two-dimensional scan, and this would be for diglycine, scanning one dihedral angle here between -180 and +180, and the second one also between -180 and +180, and we get a Ramachandran plot. The lowest energy region of our plots are displayed in red, and so here we've got the carbonyl groups twisted from one another, and this forms the basis of an alpha helix if we were to add on more amino acids. The highest energy region, indicated in blue, have eclipsed carbonyl groups, and so there's electron-electron repulsion. There is another low energy region right here at 180, 180, and that's a planar structure which forms the basis of a beta sheet. So we can understand, again, what MOPAC has calculated in terms of the molecular structure. In inorganic chemistry, since MOPAC has access to so many elements, you can build up many different molecules. WebMO can display the symmetry elements of it, not only of simple molecules like this, but even of buckyball and things of that sort. And WebMO allows us to visualize the MOs that are calculated by MOPAC. In this case, back bonding between a d orbital on a metal atom and the pi anti-bond on CO gives us overlap. here, which leads to the very strong bonds between CO and metals. In physical chemistry, we use at Hope College computational chemistry to compute potential energy surfaces, curves in this case, for HCl, which every physical chemistry student measures the spectrum of. And then we can actually do a high resolution calculation at the bottom, which I did with PM6 and MOPAC here, and get out the leading quadratic term, which is 1/2 K, the force constant, in units of kcals per mole, that's MOPAC's units per angstrom squared, and do a little unit conversion to get a force constant from which students can then calculate what the molecular frequency, vibrational frequency is, and compare it to experiment. MOPAC is also great at locating transition states. This is a keto-enol tautomerization between vinyl alcohol and that proton being up here, that proton being transferred down here to acetaldehyde. And we're looking at the normal mode of that process. Now, most of these jobs took, in fact, less than 1 second. The longest jobs took about 10 seconds. Those were the Ramachandran plots, where we did an optimization across 2 dimensions, and also the optimizations of phenolphthalein. This makes the MOPAC-WebMO combination extremely useful in large lecture classes or large lab classes. We have many students doing calculations at the same time, or almost the same time. The last item I'm just going to touch on is the wide variety of implementations, how MOPAC and WebMO can be deployed. Of course, the classic approach is to put the computational chemistry program, MOPAC, and perhaps others, and WebMO on a server, which could be Linux is what we recommend, but also we support macOS and Windows, and then all the clients can access them over the internet. An increasingly popular approach is, instead of having a physical server, is to create a cloud instance of a server on either Google Cloud Platform, Amazon Web Services, or Microsoft Azure, and then use and then install MOPAC and WebMO up in the cloud. In fact, we provide a script called SITC, Server in the Cloud, that automates that entire process. You just create your server, and SITC will install WebMO, OpenMOPAC, configure the 2, and you can log in all within about 2 or 3 minutes. The cost of a production server for teaching, at least, is about $1 a day. So if you wanted to run a lab or something of that sort, that might take a week. It's less than $10 and far less than the chemicals you might use to run another type of experiment in a general chemistry lab. One can also install MOPAC and WebMO on an individual laptop or desktop. In this case, one installs not only WebMO and MOPAC on your system, but most likely you'll need to install a web server, Apache typically, and Perl, which is what WebMO uses as the interface language. Then your laptop or desktop becomes both the client and the server, allowing you to run on an individual system. Finally, WebMO distributes apps, free apps for both iOS and Android devices that allow you to build and submit jobs from your phone. So, if you're sitting in a seminar and you want to do a quick calculation on something, you can just do it on your phone and quickly check out something. I've done that on occasion to see what a speaker is referring to, or to get some more information. Okay, so in summary, the combination of MOPAC and WebMO is useful because it lowers many barriers, particularly accessibility. Anyone with a computer can just simply log into an instance of WebMO and run calculations. Resources, MOPAC is so efficient that we can run large jobs in small periods of time, and both WebMO and MOPAC are very low to no cost. And technical expertise. Both MOPAC and WebMO were designed for the non-experts, and so the combination really is a natural one. MOPAC and WebMO allow non-specialist researchers to address chemically interesting problems, and they are suitable for use, I hope I've demonstrated, throughout the entire undergraduate chemistry curriculum. I invite you at your leisure to just go to the WebMO website and log into the working demo as guest, and you'll be able to try out WebMO using MOPAC or any of the other engines and see how it works out for you. That's what I have for now. Thanks very much. I'd be open to any questions.
All right, thank you for the talk. So now we're entering into the discussion section, and we can leave that with WebMO specific question and discussion, and then kind of broaden it out to the more broader discussions. Does anyone have any WebMO specific questions to begin the discussion section off on? People aren't really being chatty. And this is kind of a weird system of virtually raising your hands. So maybe people aren't completely used to it. Yeah, so how does, is MOPAC the main low cost solution? Or are there other comparable things? Like I think I noticed on your list, you now make XTB available. So that's presumably also of a comparable cost as another semi-empirical code, for example. So there's competing options out there, but is that connected up with all the features, for example? Like are all the engines interoperable for most of the functionality on WebMO?
That's a great question. So WebMO supports both free and commercial software. Basically, so for example, in the commercial world of ab initio chemistry, Gaussian is supported, but so is Orca. And so users have a lot of choice. In the semi-empirical world, MOPAC is by far the most popular program. In fact, it is the second most popular program, second to Gaussian, that users use on our working demo, primarily because of its performance and the ability to run large systems. Also, our working demo has a 30-second time limit. So you can do a lot with MOPAC in 30 seconds. You can't do as much with the ab initio programs. Yeah. Now, that said, in terms of interoperability, the a feature of WebMO is that it presents a relatively uniform interface, irrespective of the underlying engine. So one would set up a coordinate scan the same way in MOPAC as one would in any of the other programs. So once one learns how to sort of set it up using one program, one can then use other programs as well. And that again is a great use case for MOPAC, because you might use MOPAC to do an initial geometry optimization of a very large system. And then perhaps if you needed some higher accuracy method, you could then follow up with that. Because the jobs naturally sort of flow into one. You can use the results of one job to feed into another job, even if the underlying engine is different. So we have sort of strived to, what do I want to say, represent all of the functionalities, calculation types, as many as possible for each of the engines. I will say that you're right, XTB, we just added support for this spring. But in the terms of the types of jobs that can be done, MOPAC is far superior in terms of the many, many different types of calculation types that can be done.